right, thanks everybody for coming despite the nice weather outside and the summer that's starting. Well, starting a month ago, but good to hear. So this is going to be the last CENTRA seminar of the semester. We will restart them in September. Before that, today, it is my pleasure to introduce our speaker. So I'm talking about Guillermo Lara. Guillermo did his PhD in CESA in Trieste, and currently is at the AI Institute in Potsdam in Alessandra Bonanno's school.
Thank you, Alex, for the introduction. And it's always nice to come to Lisbon. And yes, it has been nice to interact with you. So yeah, I'm going to talk about dynamic conditions in a beyond GR theory called KS. It's based on work done in collaboration with Miguel Lara, who used to be at CESA, now is at University of Nottingham, and Marco Pisosami, and my advisor, Barroso. So before talking about beyond GR, I want to give credit to good old GR. So GR is actually a good theory of gravity. Here, yeah, I put the equations in motion of a classical GR. And the point of this plot is to illustrate that this theory has been tested in a wide variety of scales, regimes, and systems. So what you see here is the binding energy against the characteristic speeds of different systems. And in the color scale, you see the characteristic types of different systems. And for instance, you can see that general relativity has been tested, in the bottom left corner in the solar system. You also have the CMB test around here. And more recently, you have a sound gravity test in the top right corner, like the gravitational waves from the LIGO and Alcagra collaboration. So first of all, I want to spend some time motivating why you might want to think about beyond GR. So I put 3 different reasons, but there might be more. It's not a comprehensive list. But first of all, you might be pushed outside of GR by physical principle. By this I meant, for instance, the clearest example is that in the rest of physics, we know that the fundamental description of all of the other 3 forces in nature is in terms of quantum fields. So it would be natural to expect that gravity might also have a quantum description. Yeah, this might inspire some modification to GR. Second reason, I thought you might want to solve a problem elsewhere in physics. So for instance, in cosmology, we know that most of the energy content of the universe is practically unknown. And one of these components is dark energy, which is responsible for the self-accelerated expansion of the universe. So if you don't like a cosmological constant, fine-tune cosmological constant to explain this, you might want to modify gravity to explain this dynamic. And then as a final reason, you might want to better understand GR itself. By this I meant when you question the pillars which general relativity was built, you might end up understanding it better and its successes and why it's a good theory. So let's say once you've decided to go beyond GR and you're considering a particular theory, you might also want to check that it satisfies some desirable properties. So for instance, whatever theory you propose should reproduce in terms of GR, then the observation. It should not just be a more complicated theory. It should describe new phenomenology. For instance, it might predict the existence of new compact objects, such as, let's say, stable scalarized objects. And finally, this theory must be theoretically and mathematically consistent. And one example of this is that it should be a theory that makes prediction, that has perhaps some sense of causality. And during this talk, we will talk this concept. We will touch this concept of well-posed system. So let me move on. Yeah, I just wanted to give one last motivation. Why would you want to go beyond GR with numerical relativity? Why spend all the time and computational resources to investigate this series? Well, one motivation is very similar to that in GR. Like there is some phenomena where nonlinear effects are important, and the only tool available is using computers. In GR, this might be to get the weighting to merger of compact binary coalescence. And in alternative theories, this could even happen before the merger of the objects to describe, let's say, nonlinear phenomena such as spinning, which I will tell you in a bit. So the outline is the rest of this talk is the following. So I will try to explain to you what is the main problem for going beyond GR with numerical relativity. For the relative is the lack of so-called well-posed simulation, and some solutions that have been proposed. Then I will tell you a little bit about quiescence and why it is an interesting theory. And then finally, I will touch on illustrating with this theory quiescence some of the ideas of the first one. How what might seem like ill-posed dynamics can be rendered helpful. Yeah, and in this picture I just illustrate there's many different kinds of alternative theories of gravity, and quiescence lives in this corner around here. More specifically about the last point, what I really want to answer is the following two questions. When things go wrong, which I will define later, can we extend the theory in some way to cure these problems? And particularly, I will be referring to a UV completion, which, let me just give a hand-wavy definition of what a UV completion means. Basically means I want a theory that has a larger range of applicability that can reduce to quiescence in this example in some kind of way. And that hopefully will be helpful. And I would like to compare standard UV completion with a popular approach these days, which is called the fixed notation space. And you can find all the details about this in the paper. So let me start with trying to illustrate what is the main problem. So what can possibly go wrong? Why can't I just take, let's say, my favorite alternative theory of gravity and just write the equations of motion in the computer and then press a button and evolve? Well, you might, let's say you want to simulate the binary input of star in quiescence, and you start, let's say, maybe you can evolve for a while in time, but at some point you might get an error in the code, and things blow up, and the code crashes. And then you need to ask yourself, what is going wrong? Is this physics? Is this mathematics? Is this a bug in the code? And just to remind everyone, like this can even happen in general relativity. So this is a plot from a book in numerical relativity. And here, what the system that they are simulating is basically general relativity in a box. And you add some random noise perturbations in the Cauchy space. And then you see that it actually depends on the particular way you write the equations of motion, whether you can perform a stable simulation or not. For instance, if you just naively take the ADN equation of motion in 3 dimensions, you might get, let's say, option one way of writing the ADN equation, for option 2. And you might see that some, let's say, quantity blows up because it's finitely stable. However, there is some other way of writing the equations of motion where you can perform a stable. So in this case, the answer is it is a mathematics. So just let me be a little bit hand-wavy still. So what kinds of equations can we actually easily study in the computer? So I put here on the left-hand side, like physicists usually like the what's it called, harmonic oscillators, and this is like the next approximation to it, like the wave equation. So wave equations are nice; they satisfy a property that they are hyperbolic, meaning this box operator more or less looks like hyperbolic the equation of a hyperbola. And these kind of equations usually have a smooth solution. However, when you go beyond GR, often you find the modification picture. So you might get, let's say, on the right-hand side, something that might look like a wave equation, but it's a little bit different. Instead of this box operator being described just by the metric, spacing metric, let's say we deform it by gradient of field. And then also sorts of things can happen now. This equation can start healthy and then dynamically become what's called parabolic or elliptic. So if you take this operator, it might look something like this, and then this value of lambda can go to 0, and it can even be negative. It might end up looking like Laplace equation actually. And also this kind of equation might lead you to shocks or solutions that are not smooth. Okay. We go to gravity, there's a similar picture. So gravity in general is harmonic gauge with like a wave equation. It's also easy, it only took 40 years to solve. And then the same applies here. Then if you go beyond GR in the metric sector, then you might get something that is ugly. For instance, for scalar Gauss-Bonnet or effective theory. Besides the equation changing character, you might also have the issue of having to deal with higher derivatives and fully small. Let me be yet a little bit more precise. So the minimum requirements you should ask of your equations before you put them in the computer should be that they satisfy that there is a well-posed initial value problem. The initial value problem essentially is you start with some data at time 0, and you want to use the equation for motion to propagate this in time, hopefully get prediction T1. So you want that when you do this, the solution exists, that it is unique, and it is predictable, and this other property that is continuous. In practice, this is a very mathematical definition and it's difficult to prove. So what people do in practice is they prove that the system is strongly hyperbolic, meaning, let's say, sketching it more or less, means that you can write your new equations of motion in this way, where you pack all your whole variables in this vector U. And this system has the property that is plus linear, so there is no product of derivatives. And there is this matrix M in front of the spatial derivatives, which is called the characteristic matrix. And if you said that the system is non-hyperbolic, this matrix can be diagonalizable, and the eigenvalues are real. And these eigenvalues are often called the characteristic velocity. So then there are some mathematical theorems that bring you from some hyperbolicity to having the nice properties I alluded to before. Of course, you can find this. David has written about this, so you can find all of it there. This is not the only problem. Like once you've dealt with the mathematics, there's still maybe a bunch of problems in the numerical implementation. You need to basically rethink everything you did for GR, from the initial data, from the type of method you're going to use to discretize the system, from the conditions, and even how you extract the physics out of it. So let me just describe some ideas of the progress done in recent years. So picture again this modified wave equation that I described in the not so easy part. So in this paper, Figueras and Franca of 2020, what they illustrated is that, okay, maybe one strategy is that you could take this equation and then you could explore the parameter space in couplings and initial data and map out the healthy regions where the theory is well defined. So in this picture, this would correspond to the blue region. I won't describe it because basically they are studying gravitational collapse in spherical symmetry. And the black line here means physical collapse. So they're trying to avoid that. So the blue region is the healthy region, whereas the yellow region and the green regions are ill regions. So in this approach, you might, with each theory that you propose, you will attach to it its range of applicability, and the range of applicability will be this root. However, this in practice is quite easy to do. Maybe you wouldn't expect to do it for every possible theory and for every possible configuration of the data. So you might want to think about something else. So there are three other popular ideas. So the first one is basically, okay, you want a well-posed formulation, well, go and find someone and prove that there is a well-posed formulation. And luckily, some people have proved that if you choose a particular gauge, you can have a well-posed formulation in this gauge for a large class of theories called Lovelock and Horndeski. This approach, however, only works at weak coupling. Here you can illustrate the auxiliary method with respect to the physical method. There is also an extension for the CENTRA board that is analogous. Then a second idea might be, okay, we know that from the 40 years of experience, we have the GR, we know how to deal with GR, so maybe we can expand perturbability around it. So this is basically the reduction of order approach. And in this way, by perturbing around GR, the perturbations might inherit the healthy features of the principal part or higher availability terms of GR. So in this work by Okungova 2020, here you see the zero order perturbation, you have just GR, binary black simulation. At first order, they can compute what is the dynamics of, in this case, dynamical Schoenstein scalar field. And then they can use both of these to inform what are the perturbations to the metric. And at every point, all of these equations are thrown ahead and body. This suffers from secular effects. To disadvantage. And then finally, the last idea in the business would be the fixed integration approach, in which, let's say, you write the modification to general relativity as scaling with some coupling epsilon that might be small. And then the idea here is to deform the theory by introducing an additional variable, here pi, and prescribing an additional equation that would smoothly make pi follow the original and variable within a time scale tau. So the hope in this last case is that by introducing this time scale, you will be damping out frequencies that are larger than 1 over tau. And hopefully we will continue here. So with these ideas in mind, there has been a lot of work in recent years. Like compared to 10 years ago, a lot of simulations have now come about. In Horndeski theories, in the Institut, in GR, Schoenstein, automatic gravity, also Newton star simulations. And you get these pretty pictures up here and down here. Of course, there's other classes of combat objects that have been simulated in this moment, like Boston charge, etc. So it is an active area. And then even I myself, I recently started working on like simulating killerized black holes in this sense. Killer Galvanic theory of gravity. Here, in collaboration with the SXS people and Carl Pfeiffer. Yeah, here I'm illustrating just a scalarized black hole and scalar rate. But let me now be more specific. So let me go back to here. So now I want to illustrate these ideas with this. So K-essence is a type of scalar tensor theories described by this action. You introduce an additional degree of freedom, which is scalar field, phi, right? And if you write this action in the so-called Einstein frame, then you get the following: you have the usual Einstein field action. And now this function k of x that would describe both the kinetics of the new scalar in terms of x, which is the kinetic term, and also it could provide derivative self-interaction to the scalar. So you might have, let's say, powers of x in this function. Okay. And then finally, this scalar can couple to matter conformally, meaning it enters multiplying the matter in the matter section. This theory is motivated from cosmology because it can be a dynamical explanation for dark energy, and it's part of a very general framework for the new theory of dark energy. It is a theory that remains viable after the observation of the neutron star binary merger, TW 1708-17, that told us that gravitational waves travel at the speed of light. And it also viable after theoretical constraints telling you that gravitational waves don't become dark energy. You can take this action and derive the equation for motion, and you get the following. You get something that looks like Einstein equation, sourced by stress energy tensor of the scalar and the stress energy tensor of matter. Here I'm omitting the matter equation. And then you get this modified wave equation that I was alluding to. This wave equation depends on an effective metric that is defined here below. It is a deformation of the usual spacetime metric multiplied by some function that depends on gradient. This will be again problematic. The phenomenology of compact objects is the following. The black hole's solutions are the same as in VR. There are nonlinear theorems for non-spinning, unspinning black holes. And the interesting bit is actually the math. So neutron star can support scalar hair. And yeah, if you're a bit familiar with the traditional scalar tensor theories, you might say, okay, but scalar tensor theories are very well constrained by binary tensor observations. Well, if you look more closely in the theory, it actually turns out that there is a so-called camouflage or thinning mechanism that suppresses an additional scalar force in the vicinity of the neutron star. So that you would expect that the theory would pass a binary tensor constraint. So there is this region around the neutron star where scalar force is suppressed, and it goes up to a radius called the swinging radius. And in the exterior, you can see again the scalar force, and you can drive cosmology. If you plot the scalar force compared to the traditional scalar tensor theories, you see that the k essence is the red line, and the scalar force is expressed compared to the green line, both inside the star, which is before this point, and also outside. And here, there's no spinning, so the two lines match. This is the scalar force against it. And there has been a lot of work done in matter by people at CENTRA. Yeah, both in vacuum, both in matter, they have done pretty simulations of the essence and for binary neutron stars. However, here I will focus on vacuum. So let me take a very simple model now. I will take quadratic k essence, which is defined by this function k of x being the standard kinetic term, plus a first nonlinear interaction. And the statement is that if you evolve this strong hyperbolicity property will fail dynamically, generically. So even if you start with healthy initial data, it could happen that it can evolve into a nil false state in finite time that is not necessarily hidden under the function, like non-insoluble black. So to begin diagnosing these problems, is very useful to start as simple as possible. So we will start again with vacuum spherical collapse, where generically I'm thinking of taking a scalar shell and letting it fall into gravity. This has been studied in KS and planar 2011, however, they not very much aware of what the issues. So what happens? So if you take the system, again, I will mostly be concentrating on the scalar part because the metric part is, we know how to deal and it looks like Einstein equation. So I will mostly be talking about that now. So you have this modified wave equation, and I can write it in first order form. So I described it before in this way. And then I can compute the eigenvalues of this matrix time, which I said were the characteristic velocity. And these I denote by d plus and d minus. Then I will plot the maximum and minimum values of this against time. then let's focus first on the left-hand side. So when you take the positive coupling of the theory, what happens in this particular example is that as the scalar shell collapses, these characteristic velocities begin to approach each other, and somewhere in space-time they coincide at some point. And thus, it means that this matrix becomes, yeah, it's like values are the same, so it stops being diagonalizable. So at this particular point, what happens is that this wave equation turns parabolic. Then beyond this point, which we cannot evolve, it becomes elliptic. And this is usually called a trichotomy problem because it looks like the properties of this equation. Instead, for the other sign of the coupling constant, which is the right-hand side, what happens is instead of becoming degenerate with characteristic fields, what might happen is that one of them goes to infinity. And this is often called a Cauchy problem. Again, because there's an equation that more or less describes it. So, having seen that there are problems and we cannot continue. Yeah, and then just as a bracket, this is not a problem unique to KSM. Actually, there's a very interesting connection with massive vectors, self-interacting massive vectors. Some people have recently, with authors, tried to evolve self-interacting massive vectors to study superradiance or to study other systems. And they have found that for some types of self-interactions, the code crashes, the system is unstable. And then in this paper, we argue that, okay, you can actually reintroduce a gauge invariance to this series with this particular mechanism and see that this massive vector theory turns into a theory with a massless vector and KX. And then you can use the tools that we developed for KSs to diagnose that okay, the system is unstable because, you know, in this picture below, it's actually equal. This was just an interesting connection I want to highlight, but let's return to just here. So I showed you that there are some problems in the evolution. So I'll go back to the questions I want to answer. Can I extend this theory to give healthy dynamics, and how do the standard healthy extension compare with it? So one way to extend this theory is by taking these Higgs equation. So you consider a scalar, now a complex scalar field, described by this action here. Complex scalar field psi has a standard kinetic term and is subject to a potential, which is describing this picture. This potential has two critical points, one unstable maximum and one stable minimum. And of course, you can take this action and compute the equation of motion, and for the scalar, you just get Klein-Gordon equation, which is on the EC side of the equation you can manage. However, if you expand around the minimum of this potential, separate into a phase mode going around the path and the radial mode in the radial direction, you can actually identify the KS into the phase mode. You can take the equations of motion and solve perturbatively for the radial motion, and then insert them back and actually derive the equation for motion for KS, and also derive what are the couplings. So in this sense, K-essence is, yeah, the UV completion of K-essence is this Higgs theory in the limit of large n. You recover K-essence in the limit of large, where m is the mass of the volume or the Higgs. So, and then finally, the second approach, fixing equations, would be, okay, now take the scalar equation, motion, again, given by this vector metric, and identify the problematic part. Turns out you can write this equation in this way, in a conservative form, as right hand. Then the prescription of this fixing equation is like, okay, the problematic part substituted by an extra variable, sigma, and now prescribe an additional equation that would make sigma follow the value of k prime. in some way you're introducing an additional degree of freedom, so you might ask yourself, okay, is this trying to imitate a proper decomposition like the one here? So then
What is tau?
yeah, sorry, tau, maybe I didn't say it before. So tau is an extra parameter. So actually, you have some freedom in choosing this equation. The only idea is that should be an equation that should drive the sigma to k prime. So for instance, in this choice, there is one additional parameter. But the idea is that if your results are robust, it shouldn't depend too much on the value of tau. So maybe tau is related to the size of the system you're studying, but should be a range of taus and different types of drivers that should give the same effect.
So, in this approach, basically, sigma will like behind with
Yes, and that's how much it lags depends on this time scale. So if this time scale is very small, then it should follow it closely. Yeah. So you should take this tau, probably to be smaller than any time scale of any observable that you want to observe out, which is the same time. So I don't know, if you want to do a binary, you might want it to be much smaller than the orbital times.
Okay, but then the limit of tau going to 0, you end up again with tau.
Yeah, this might happen. Yeah, this is an accurate error. So yeah, maybe you shouldn't take the limit exactly to 0. But yeah, let me continue. So yeah, I just wanted to say this trick has been applied before in the case of collapsing neutron stars. In a case where actually we didn't need to apply it before. It turns out that in this paper they applied the fix in 1D code, but actually could solve the problem exactly in 3D by a suitable choice of gates. And basically they show here that they get the same result pretty much. So we want to see whether we get the same. So just to recap, I'm going to take the 3 theories that I just described, and I'm going to evolve the same system, and then I want to compare it with what I get. So I take my Gaussian scalar shell that I want to let collapse. This is the initial state. On the one hand side, I will pass it to the K-essence equation, and I will evolve numerically. For the other theories, I will convert to the variables of the entropy theory, use equations of motion of that theory, and then reconstruct the end finally compare. And yeah, let me show you just 2 cases. So the first case I want to show is the weak data case. Basically, the scalar shell has small enough amplitude that is a small perturbation from the Gaussian space. So what you see here is in the 3 colors, the 3 different theories, and time evolves up to down and left to right. And then here I'm plotting the scalar field with k by r against the radius. So what you see is that the scalar pulse in the 3 theories is basically indistinguishable as they collapse. So in this sense, all of these theories are describing the physical k-essence for weak data. You can go and compute the eigenvalues of the effective metric and see that it doesn't change character because none of the eigenvalues actually cross the 0 line, so it never becomes parabolic or elliptic. You can also compute the characteristic speeds, bottom panel. And in this case, there are no issues. None of the speeds go degenerate. None of the lines touch each other. And none of the lines also go to infinity. So this is a perfect result. You can also compute some relative error measure comparing the scalar field profiles in different theories. So you can compare, for instance, k-essence with the Gibbs completion in red and normalize it by one of them. And then here, this is this relative error measure against time. And you see that probability is below 1. And then the orange line indicates whether you've entered the nonlinear regime where scalar self interactions are important compared to the kinetic term. And again, you see that this is a weak data case, so you never get from scalar. But okay, this is a kind of a boring example. So now let's go to the strong data case. What happens when I pump up the energy of the initial data? So we'll take a scalar that has now a smaller width and has a larger amplitude. Then here again, time evolves from top to bottom. And here at the beginning of the simulation, all the three theories agree. But if you notice from the first panel to the second, the red line has disappeared. That means K-essence can no longer continue from this panel to this bottom panel. And that is because we have entered the Cauchy breakdown. So if you look at now the right-hand side, what you see is that if you compute the eigenvalues of the effective method, you see that one of them crosses zero. So at this point, the equation is becoming parabolic. And if you compute the characteristic velocities, you see that they touch. So again, the same thing. Like the cones of the scalar are doing something strange. It goes in like from. However, you can see that from this to this, the UV completions have no issue continuing the evolution by construction. This is how we constructed them. And moreover, you can see that there is nothing special going on. Like there is no high frequency features appearing suddenly at the breakdown there. So we say that it's smooth. The breakdown. We can continue it. Yeah, you have question. Yeah. So.
Okay. So I mean, on the plot on the right,
Yeah, right.
it seems as if the other theories also start.
Yes, yeah, this is a bit confusing. What I've been doing, what I did with the other two theories is I've taken the evolution values of the field to reconstruct what the eigenvalues would be in the truncated theory KF. So this is like fictitious because these are not the real speeds of the UV and the fixed theory. I just wanted to see that they were reproducing the same physics by plugging in the data in the same formulas as for the red line. But the characteristic speeds for the green one and the blue one are the same as in GR, so they are with the speed of light and just multiplied by the lambs.
Okay, but is there a reason why you stop there, or could you go on?
Because the system. Yeah, no, it's nonsense. Like you can still get values for this, but they become imaginary and stuff for the green and blue line. So yeah, I mean the picture breaks down, right? Like they mean nothing afterwards. So then you can continue this evolution. So now we have the first two panels that I showed before, and now continue the evolution below and to the right. And then what you see is that as the scalar field collapses into the two theories, they form a black hole at this point, where you see the solid line. And then there is some radiated scalar. And okay, we haven't done disclaimer. We haven't done an extensive parameter search of all the possible fixings that you can do for the theory. Just stuck to this particular equation and explored a range of parameters between pi equals 1 to 10 and got similar results. So at least we can say that at least this fixing is, let's say, sort of a sanity test of the fixing scheme, because at least it follows qualitatively what, let's say, a proper UV completion, the green line would be.
Sorry.
Yes.
What are the, sorry if you said LLS, what are the vertical lines?
Yeah, maybe I didn't explain carefully. So dash ones are the so-called scalar horizon, no, sound horizon, which is basically now the scalar and the metric have different propagation speeds. So this is basically the point where the cones of the scalar tilt.
Mm-hmm.
So, and then you see the metric horizon appearing later. So, like beyond this point, scalar perturbation shouldn't propagate out.
Mm-hmm. Okay.
And then beyond this point, the solid one, metric perturbation propagate out.
And here, like from this plot, one can see at some point, like the actual data from the evolution with the fixing the equations are different at some point.
Yeah, they differ. Yeah. So this is underestimating the radiation in amplitude, and it's also a little bit off in the final mass plot. So yeah, we can try to quantify this after, right? we did before. We can write some relative error measure. We can compare the different scalar field profiles and normalize them. Here we plot this quantity at the sign. As I tried to describe at the beginning of the simulation, everything agrees. So we have this quantity that's very small. At some point, we have the Cauchy breakdown. We cannot compare anymore with KSM. So the green and red lines disappear. Then we can only compare the two completions. And they have, yeah, as you noticed before, they have quite some differences, but they more or less like the same. So yeah, our result is almost qualitative. Yeah, and then this star means that yeah, most of the difference between the two completions gets worse beyond this star, which the star means the nonlinear regime. This is the point where the nonlinear self-interaction of the scalar is around the size of the leading kinetic term. So you see that this occurs after the breakdown, and after this point, disagreements. So yeah, I can just tell you, I'm basically done, but I can just tell you a few related ideas. So this Higgs UV completion is not the only UV completion you can do in the system. There are other options. And after some point, they might give different answers. So in ongoing work, we'll be studying another kind of UV completion, which is the following. So instead of introducing an additional complicator, we stick with the essence, but we stick with another functional form of it. So now this function k of x, which is Dirac-Bonnian completion, has this shape, and you recover again quadratic essence when you expand around small n. So here is the expansion, but you get an infinite tower of that. This case doesn't have a trigonometric problem, you can show that, but you might have other issues. You might have to tell this problem, and we're finding that it has different issues. So actually, you might not support the system of collapsing neutron stars. We find that although the characteristic speeds initially at time equals 0 are not infinite, we find extremely large values that we cannot have. So this is almost like a pathological situation, but not quite. It's bad enough that we cannot see it. But with this, I want to complete. So try to show to you that you can extend these quadratic essence in two different ways that agree in the elliptic regime. We can use them to evolve past the breakdown of the theory, which is in a smooth way. And then finally, you can use this proper unit condition to compare against this popular approach, fixed demonstration approach, to give some sort of validity or no. However, just to comment, like this fixed equation approach, whether it agrees with a proper UV completion might actually depend on the system and the specific setting. So I wouldn't take these statements to be very general. My final remark is that I try to introduce to you some of these ideas, how we can have a handle on the evolution of the GR theories, something that was not possible 10 years ago. There are more codes coming about, and there's more problems besides this to solve. Hopefully, with next generation detectors, we have more data to hopefully draw conclusions about the nature of gravity. In this case, yeah. So that concludes my presentation.
Thanks very much for the nice talk and perfectly timed as well. Thank you. So, questions? Okay, I think David was first, then we will let him.
So if you have multiple UV completions,
Yes.
which are proper, like as you showed for the Higgs one in the last slide,
Yeah.
how are you supposed to choose between them?
No, by proper I meant like, okay, it was a bit loose on the terminology. I meant like a UV completion in the more theoretical physics traditional way. Like you can write some action for it, and you can show that there is some.
Yeah, so I can see,
Integrating
I
out.
can see if you can do that, then you might say, okay, if that type of completion,
Yeah.
one or the other, avoids degeneracy of hypervelicity
Yes.
and opposes, then you would say that any such choice would be preferred over the fixing the equations approach.
Yes, the
right?
issue is
But
that.
then how do you choose between those ones?
Yes, okay. No, this is important. Like I mean, just to remark, like you cannot play the same game. You cannot write an action for the fixing equation approach.
Yeah.
That's why I wouldn't call it a proper UV completion. And then between the proper UV completions, yeah, there might be different choices. So yeah, maybe I think it's correct that at some point they will give the same picture in let's say at low energies, and at some point they will bifurcate or trifurcate, however, entricate, however many you have.
Yeah, like it's an honest difference in physics then.
Yes, but then you would be throwing UV physics. So then hopefully you observe something, you might even draw conclusions about the generalized theory, and you wouldn't be using it just to manage to evolve the lower limit. So yeah, I think there is no preferred choice besides maybe other areas, maybe it's preferred by other experiments. And just the last thing, usually we don't have access to a proper UV condition. But
What does your metric look like?
the metric. So it's yeah, we use the
No, it's in here.
okay. So for the example I presented, we use the triple symmetry, so right system, the triple non computation, which use zero mass. So we basically just have page points.
Zero shift, you mean? Zero shift.
Yeah, zero shift. Yeah.
Yeah.
For now. Yeah, you might have some minor parts. But I don't think time are on the left. So we restrict to this kind of metrics, and the equations of motion will tell you what your gauge choice will tell you what the lapse does. The equations of motion will tell you what. And in addition, you have the scalar field, which is only. So I mean, I cannot give you an analytical function for this because these are all they are restricted to values. Yeah, it's initial data. At initial time, t equals 0.
It became your solitude
Inside the shell. So, well, I mean, it's a Gaussian, so I mean, there's not really an inside. It's just a field that has a Gaussian form at some initial radius. So the whole shell evolves, the whole thing is the scalar field. It's coupled to its neighboring points and evolves according to the equation of motion. So there is nothing special about the interior. It's just made of scale.
It's a common choice if you're doing strictly symmetric simulations. Yeah. But then you're gonna-
I was just wondering what you mean by numerical generalizing.
Yeah, okay, I didn't touch on details about this. So standard. Yeah, I don't have any additional slides, but yeah, usually the generalized harmonic gauge is a choice on the type of coordinates. So there is an equation with the harmonic coordinates like this. Then generalized harmonic, there is some function here. Then the general harmonic is like, yeah, and then you can write this, right? In terms of the important field. So, so then the generous harmonic gauge, what they do is they introduce two additional metrics. This is the usual metric. There's tilde one and a half one. So now one of the metrics will enter in this definition. It will be used to contract the token. And the other one will enter how you plug in this in the Einstein equation. Usually you plug it something like this. And this half metric will actually enter. It will be some function. Let me just write it automatically. Some function this depends. You have the metric now and this other. It's actually so more or less this is how this metrics enter, and what they have managed to do with this choice is to make to break a little bit the degeneracy that appears in the art, which is I mean, I don't know all the mathematics of it, but what I've understood from talking to the authors is that this way you can manage to make the gauge modes propagate at different speed than the physical modes, and also the constraint violating modes propagate also at a different speed. So this actually helps in the proof that you can write the system.
So I'm wondering if it's used analysis to motivation to generalize harmonic gauge in normal GR.
Yeah, it's a similar idea. Yeah. So it's a deformation of that. Yeah.
Okay. So that leaves you with some freedom to choose the gauge source function, which I think you denote by those gauge functions, right?
You have some freedom to choose here, and you also have some freedom to choose how
the metrics.
these metrics are.
So my follow-up question is, you said that with this modified generalized harmonic gauge, you have like a set of alternative theories that give rise to well-posing development problems.
The small group.
I think that's what the
Small group. Yes, there is a class.
Yeah,
Log, which are, let's say, the generalizations of GR five dimensions. Horndeski, which is scale constituted for second order.
Okay. Yeah, I was just wondering whether the initial value problem is well posed, regardless of the choice of those functions, the edge. Because I suppose if you change the game.
So what do you mean about regardless? Like, because even in GR it depends how you write it.
But then what you mean in the slide is there are some gauge source functions for which you have a well-posed initial value.
Exactly. You can choose what they found in the book. My work. I'm not saying it should work, but it's more like it work. And yeah, some people have done a Cauchy. This work at small coupling. It might happen that in case the coupling constants doesn't work anymore. Basically, the proof assumes that it's a perturbation around GR. This the GR can be put in some hyperbolic form, so this is kind of a deformation around GR. So if you go too far from it, it might fail this problem.
Any other questions? So maybe I can ask a special question. I mean, you may not know the answer, but so I was curious about like these Sticomi type and Kelvin type of instabilities. Like they appear, are they the common instabilities that one may encounter with trying to simulate different types of modified fields of gravity numerically? Or from what you know?
Yeah,
From your.
I mean, they are useful. At least From what I understand, I mean, it's kind of a, let's say, toy example. My industry, how the trend of instability in more complicated theories. And I think, yeah, the concept works very well, at least for the essence and scalar Gauss-Bonnet theory. Maybe for higher derivative theories, I don't know if that will be useful. Because these Trigonian Keldysh equations are second order. And they have no dimensions. But, yeah, I think it's just a useful class.
You have some questions this semester? All right, in that case, let's thank our speakers.
If you enjoyed the video, like and subscribe.